Howdy, this is Andrea, and in this video we're going to be talking about factoring sum and difference of cubes. Sum and difference of cubes are also special cases of factoring, and we've actually talked a bit about the difference of squares, and this is just kind of one step further. So let's talk about what the heck is difference of cubes. So basically we have, not difference, sum and difference I should say. We have a sum of cubes, which is exactly what it says. It's a cube, two cubes, so a cubed and a b cubed, and a sum means addition, so the addition sign in between. We also have difference of cubes, so it's the same thing with the subtraction sign in the middle. And if we can recognize these expressions as special cases, then we can just simply plug in, we'll have to find our a and our b, but then we can just plug in the numbers and variables into our special case formula. And we've got two of them you can see here. So we have the sum of cubes, and of course we saw above that's a cubed plus b cubed. And then over here you can see we have the this is the special case formula that we would plug it into. We've got quantity a plus b times the quantity a squared minus ab plus b squared. For a difference of cubes, you can see it's almost the same thing. We've got just some minor changes in one of the signs. So how do we recognize difference of cubes? Well, it's very, very similar to difference of squares. Remember, in difference of squares, our numbers needed to be perfect squares, and in difference of cubes, our numbers need to be perfect cubes. In the difference of squares, we had exponents that were divisible by 2, and in sum and difference of cubes, of course, our exponents need to be divisible by 3. And that's simply because of the power rule. Product rule. My goodness. Okay. Let's just talk briefly here about a perfect cube. So remember when we talked about perfect squares, those were numbers that when you take the square root of them, you were going to get an integer. So not any, no decimals. Right? So perfect cubes is the same sort of thing, but what we do is we actually take the cubed root, so we show it like this. Cubed root, for example, cube root of 1 is just equal to 1, because 1 times 1 times 1 equals 1. So here we are back at this perfect cube here when we can kind of show that this is kind of the check. Okay. And let's go up here. We know that there is no perfect cube of 2, okay, or 3. If you just try it, you can take the perfect cube of 3 and you're going to get 1.44 something. Okay. The next perfect cube that we have is 8. And if we cube root that, we're going to get a 2. What that really means is what integer, when I multiply it by itself 3 times, comes back to that original number. Okay, we know that these roots here, these are roots. These roots have to be integers. They cannot be decimals of any sort. Okay, and on your calculators, you guys, if you have the TI-83 or 84 series, anything like that, you guys can just go to your math button, and you should see, once you hit that math button, somewhere in there you should see a cubed root. You would just go down to that one. On mine it's option 4. You would just go down and push enter, and all of a sudden you'll see the cube root appear on your screen, and then you can just put whatever number in here and you can double check it. If you're having trouble on your calculator trying to find the cube root just to double check something, there's a couple of different things that you can do. I want you guys to remember, I don't know if we talked about this or not, or maybe you've had this in the past somewhere, but when we have radicals of any sort, when we have a square root, it just means a number to the 1/2. Okay, so for example, I'm just going to go to a square root. We know the square root of 4, right, is 2, right? But we could also say that 4 to the 1/2 power is also equal to 2. And that's because a square root, we don't really write the 2 up here in what we call the index. We don't write the 2 in there. It's just kind of understood. But there really is a 2 in there. And so if we were to kind of expand that to this idea of cube root, well, we could say that cube root of 8, of course, we know is 2. But we can also just put an 8 into the calculator. We'd have to put a parenthesis in terms of how we would put that in. It was parenthesis 1 divided by 3 because that's 1/3, 8 to the 1/3. And it's going to spit out a 2 as well. Okay? So that's one way that you can find out if a number has a cube root. So if that number itself, the original number, is a perfect cube. And so, you know, if you have the actual original number, that's kind of the best way to do it. If you wanted to turn it around the opposite way, you can actually say, all right, what is 1 to the 3rd power, right? And if you don't have a 3rd power there, you can use the caret button. 3, it's going to spit out a 1. Okay, well, this is a cubed root. 2 to the 3rd power, okay, it's going to be 8. Well, here's our next cube root. 3 to the 3rd power. This is on your calculator. That's why I'm writing out the little caret button here. It's going to give you 27. So 27 is our next cubed root. So I would suggest that you kind of play around with that and get comfortable with your calculator. Get comfortable with how you find square roots and cube roots. All right. So how about the steps for factoring difference of cubes? Well, they're very, very similar to the steps for factoring square roots. Let me get rid of a little bit of this here. We see that in our original formulas up here, we've got A's and B's, right? So we need to find our A and find our B. And how we do that is we can see that A is the cube root of whatever our first term is, so the A cubed, and the B is the cube root of whatever our second term is, which is B cubed. And then once we find our A and our B, we plug into the correct formula, meaning if it's a sum of cubes, we use that formula. If it's a difference of cubes, we use the other formula. Now, of course, we always need to be careful of these two things here, right? We need to be cautious that if we have a GCF, we have to factor that out. If we have a negative in our leading term, we always want to factor that out. And then at the end, of course, we keep factoring. So sometimes we have to factor multiple times depending on what our answer looks like when we're done with the first step. So we just kind of be cautious of those two things. All right. Our second step here. So let's look at an example here. Example number 1, we've got x cubed plus 27. Well, we need to really identify whether this is truly a difference of cubes or a sum of cubes. And in this case, we can see we have an addition sign. So this is a sum of cubes, at least we're hoping. So let's check it out. Let's go back up here. How do we recognize it? Well, our numbers have to be perfect cubes. Okay, well, our number here, 27, I know just a moment ago we talked about that if we took 3 and we cubed that, we were going to get 27. Alternately, if we took the cube root of 27 on our calculator, it will spit out a 3. And 3 is an integer, so therefore we know that 27 is a perfect cube. So we're all set here to find our A and our B, which is the second step above, and to plug it into our actual formula. Okay, so let's find our A. That we know that A is equal to the cubed root of our first term, x cubed. Well, a cubed root of a cube is whatever the base is, right? So that's going to give us x. And we know that, you guys, because x times x, right? Remember the first power, first power, first power. This is a product rule. And remember, in the product rule, we are supposed to add our exponents. So that's going to give us x cubed. So you can always check it. Go back and check it. Okay, so here's our A and our B. We just talked about this. Cube root of 27 we know is 3. So we have our A and our B, and we know that this is a sum. So we're going to come back up here, and we want to make sure that we are using this right here, this formula right here, because this is for a sum. All right, so we've got our A plus B. So we're going to have our x plus 3. And then you notice we have our A, go in a little closer here, A squared is next. So if A is our x, then we've got x squared. In fact, you know, it might be better. Let me just write this above. We've got A plus B. We've got A squared minus AB plus B squared. And what we're really doing is just plugging in what we found to be our A and our B in this particular problem. All right, so we're now minus AB. Well, we don't write x3, right? That is not an algebraic way to write a variable term. We always have the coefficient first, so we're just going to flip that around. We're going to have 3x and then plus b squared. So this is going to be 3 squared, right? And if we don't want to have to write out the whole thing again, you can just simply then say, okay, well, I know that 3 squared is 9, so I can just leave it like that. I can plug that in right off at the beginning there. All right, so that was example number 1. All right, let's move on here. Example number 2. All right, so remember the two things that we're checking is that our numbers are perfect cubes and that our exponents are divisible by 3. So let's check our numbers here. We've got a 3 and a 2,187. Okay, well, I don't know about 2,187 yet. That's a pretty big number. But if we try to take the cube root of 3, we're going to get basically 1.44 or something. Okay, that is not an integer, therefore we know 3 is not a perfect cube. So we need to start looking at some options. Remember the caution up here. I'm going to go back for a minute. Remember the things we really need to be aware of and cautious about. First of all, see if there's a GCF that we can pull out. See if there's a negative. We don't have that in our example here, and we're going to try to keep factoring if we need to. So let's go back here. And let's see if we are able to get rid of this 3. Let's go to our calculators and see if 2,187 is actually divisible by 3. And if we do that calculation, we're going to come up with 729. So this is going to give us a cubed minus 729. All right, well, let's check this out. Let's see if we can find our A and our B and see if we're able to plug it into our formula. So we would know that the A is equal to cubed root of A cubed. And of course, indeed, we can see that that is just going to give us A. So that is fine. And we knew that because this exponent right here is a 3. 3 is definitely divisible by 3, so we know that that would work. All right, now our B is going to be the cubed root of 729. Okay, if you guys plug that into your calculator, we would find out that the cubed root of 729 is 9. So that tells us that 729 was definitely a perfect cube. So we're in business here. You notice this time we have a subtraction sign. Okay, so we know this is a difference of cubes, and if we go back, we can see that we're going to be using this second formula here. Let me get rid of some of this other stuff up top. Because we have the subtraction, so the only subtraction sign is in that very first parenthesis. The rest is going to be addition sign. So let's go ahead and just write out our formula. Our formula is going to be A minus B, quantity A minus B, I should say, and then A squared plus AB plus B squared. So here's our formula, and basically what we're doing, guys, is we're just going to plug these, both of these, into our a and our b. So we are going to have a minus 9, quantity a minus 9. And then we're going to have an a squared plus 9a because our coefficient goes first. And then, of course, we would have a 9 squared. And so we can go ahead and write that out as 81 if we don't want to write an extra step. And voila, we are finished. Okay, so that one was just a teeny bit more challenging. Kind of as we review here, we had to just pull out a GCF here. And then what we had here is perfect cube, so we were ready then to move forward and find our a and b and plug into the formula. All right, we have one last example here. Example 3, 64 and 8. Well, 8 is definitely a perfect cube. We know that, right? We did that before. We know that the cube root of 8 is 2. But 64, when you try to take the cube root of 64, you are not going to get an integer. So we know that's not going to work. So let's kind of go through our checklist of things that we have, some tools we have available. I know that 64 is divisible by 8. Okay, so let's do that work first. So that's going to give us an 8x to the 9th minus y to the 6th. And now my number is an 8, and I know 8 is a perfect cube, so we're good there. And let's look at our exponents here. I've got a 9. Well, 9 is definitely divisible by 3, and 6 is definitely divisible by 3. So I think we're good to go here in terms of considering this a difference of cubes. Okay, so next on our list would be finding out what a is equal to. A is going to be the cubed root of that first term, so 8x to the 9th. And I want to show you guys that really when we're doing this, it's the same. If you wanted to break this up, if you find this easier, it's the cube root of the number part, the coefficient, and it's also, so I should say times, the cube root of the variable part. Well, cube root of 8, we've talked about several times, is 2. And the cube root of x to the 9th, basically, you guys can, there's a little trick you can do here too. If we know it has to be divisible by 3, we can just take this 9 and divide by that. And that is actually going to give us what the exponent is on that cube root. Okay, and the reason for that, let's go over here and just check this for a second. We know that x cubed times x cubed times x cubed, using the product rule where we add those exponents, is going to bring us back to x to the 9th. Okay. All right, so here is our a. A is equal to 2x cubed, and our b is going to be equal to the cube root of y to the 6th. All right, well, we can do the same thing. Let's just take that little 6 and divide it by 3, which of course is going to give us a 2. So we know that that is going to be y squared, because y squared times y squared times y squared, when we add those exponents, is going to give us y to the 6th. All right, so we can plug this now into our formula. I mean, a lot of pink going on here, so let's just, now this is once again a difference of cubes. So let's write out that formula. We've got quantity a minus b times a squared plus ab plus b squared. So this is our formula, and let's just start plugging. So a is 2x cubed minus y squared. Okay, it gets a little tricky here, so be careful. You got to go slowly here. So we have a squared. So a is 2x cubed, and we have to square that. Right? So take the time to write this part out because I think it will be helpful. And then now we have plus ab. All right, so let's just say a here is 2x cubed, and we're going to multiply that by y squared. That's ab. And then we have y squared, which is our b, but you notice here we have to square that. Just like here. Just like right here, we had to square that. So that's why we have to put both of those in parentheses inside the parentheses. All right, so here's what I mean about you got to keep simplifying, right? We're not quite done yet because there's a little more that we can do here. In terms of this first parenthesis, there's nothing we can do, so we just bring that down. But here we have a power rule. We have a product to a power, so we know that this 2 applies to both the 2, so it's going to give us a 4. And then x cubed to the second power, we just multiply. That's power rule. We multiply those exponents. It's going to give us x to the 6th plus, and there's nothing to combine here, so we just simply write them, and we write the variables in descending order. And then this is going to give us y to the 4th. And if we look back at that, we don't really have anything else that we can simplify. So even though it looks like a very big, complicated polynomial here, 2 polynomials actually, it is simplified, and we are done. All right, guys, that's it for this video, and we will be talking to you soon.